Okay, so here is the decision tree for diabetes. And clear all my output. So when I run this, I want to explain a couple salient points here real quick. Where I'm just doing some installs because I originally designed this on my local machine and I wasn't sure what Colab had. So here's some more things. Now, in the past, we went from AWS SQL right directly to Google. We've also gone directly from AWS to our desktop using Tableau. We've also worked with a CSV flat file. But one thing we haven't done is go from AWS or a data set, a CSV, directly to Colabs. Now with Colabs, you can upload using Google Drive. I just put this on Dropbox. So this is just, literally if I just click it, and it will download here. Yep, see, it just downloaded. And literally, originally I downloaded it from Kaggle at first, but had problems with authentication. So here's just that data. Ooh, there's 10 copies of that data set. Well, you can't really see it, but full screen with video right here. So you just see it. It literally just downloads that data set. So, what are the advantages and disadvantages of directly downloading to a notebook? So some of the advantages is if I don't have the storage on my machine, I can do this. Also, I can do this on an iPhone, iPad, Android, because I'm not saving anything on my local machine. I'm literally going from either Kaggle or some data source directly to Colabs, and it's not SQL. I'm just moving it as CSV. It could be a JSON. It could be any type of file. So I do my import, and then literally I just grab this file and it saves it right here. Now, this just happens to be on Dropbox, so that's what I use, but it could be Google Drive, it could be a million different places. So that's very, very handy, this little, hey, and you could literally just put it in here. You can read from URL. So there's different ways to do that. I just grabbed it, put it on a shared drive. Then from the shared drive, I just put it in here. Okay, so let's see what we have. Looks like we have pregnancy or pregnant, glucose, BP, skin, insulin, BMI, pedigree, age, and label. Okay, we're going to say, hey, what do we want as our Y, our target variables, and what do we want as our features? What are we going to, what are we going to basically add together to kind of separate out this data to make our decision? We're pregnant, insulin, BMI, age, glucose, BP, and pedigree. Okay. So labels if they're diabetic or not. That's a 1 or 0. So that's this column right here. So I can zoom in here. Then what do we always do with this data set with supervised learning? We split the data set. Again, I'm doing a 20% split, 80-20. Then boom, I'm just going to do this real quick. And let's see what we got. And you see, literally, it ran that. It doesn't even count time. 0 seconds. I'm at 68.1% accuracy. Well, it's not bad, 68% accurate. But the problem is, it's not really a decision tree, Richard. I can't see anything. So if I run this right here, this is going to make me a graph. And it's also going to download it. So you'll see it pop up here with download and create a graph. Yep, there we go. So let's open that. So there we go. Oh boy, that is really complex. I wouldn't even know where to begin. So the very first one, I don't know why this black box is here. I've tried to interrogate that, try to get rid of it. I've Googled that, and I'm just going to have a black box. It doesn't bother me. The data's still valid, it's just I have a black blurb there. So glucose. Is glucose higher or lower than 127? False. What is your BMI? Greater than 29, or what's over here? Age is over 28. Then we go, hey, if your age is over 28, maybe your glucose is here. I want to zoom back in, guys. Sorry about that. So again, kind of hard to read, but still, what do we get? 70% accuracy, 68.1. That's pretty nice. So that means Let's think about what that means. That means that we're splitting our data into bins at a 68% accuracy rate. Well, that's pretty good. You got this kind of insane picture, though. What we can do about that? Well, let's change. Actually, this should be 3. Let's change the max depth. Let's compress this a little bit. Let's prevent it from branching out. Let's prevent it from having so many nodes. Look at that, 0.02 seconds. Now we're at 73% accuracy if we round up. What does that look like, Richard? Let's make a real quick graph. And look, it also downloads that. Now that is a little easier to read. So if we were to take all of our data and plot it, let me grab my iPad real quick here. Okay, when I say how to read, or this article, just look at the pictures. This is not the world's best article because they have a lot of like ads, but I love how simple they made the decision tree here. Okay, if we're looking for a simple decision tree to classify animals based on their features, we will use the color and height of the animals as input features. So color equals yellow. I'm not sure if that's equal or do not equal, depends on what language, but whatever. So like I said, it is equals yellow, so true. So we have, it looks like tigers and giraffes. Where things that are not yellow are elephants and monkeys. So we went from color and then we go to height. Is it over 10 feet tall? If it is, it's a giraffe. If it's not, it's a tiger. If the elephant is under 10 feet tall, false would be an elephant, or this node. If it's true, less than 10, it'd be a monkey. That's basically the same way. Where's the easier one to read? This one. So entropy is just a method it uses to calculate these out. This one up here uses Jenny, but you see to increase accuracy a little bit, we set the method to entropy right here, and the max nodes to 2. So that's all that is. Samples, classes, there you go. So now the next thing, in regression we talked about cross-validation or cross-fold validation. Cross-fold validation is the idea that instead of just doing a simple train test split, which I say, hey, 80% of my data I'm going to use to train, 20% I'm going to use to test. The problem is if there's some type of hidden or super valuable information in that test, then we never see it. So with cross-fold validation, you still do the 80-20, for example. We do it 5 times. And we shift wherever that 80-20 rule is. So the first time I did this, I had a lot more numbers. 10, 15, 12, 15, and 20. We'll do the same thing here. We'll do 5, 6, 8. So basically what this grid search does is basically look for optimal values. Now, Richard, how does it look for optimal values? Well, basically doing every mathematical computation. Computers are very fast at math, and this is not very, it's not a very big data set. It's 10K, something like that. Yeah, I don't even know how big it is. It's a very small data set. It is, we'll try and find it right now. It is 24K. So, I mean, just a few hundred lines. So, one second. Oh, this comma right. We need a comma right here. So basically what we can do is we can look at every combination of this. Okay. We can say we want the maximum depth to be 2. Try that. 3, 5, 7, 10. To keep going on and on again. The problem is that this becomes very, very computationally expensive. That's what I was looking for. Oh, sorry. Hold on one second. Let me add that line in there. Sorry, I originally had a lot more, then I reduced it just to kind of speed it up. So basically what we're going to do is we're going to tell it, hey, instead of just making 1 tree, make 200 trees, make 300 trees, make 10,000 trees. So grid search, using the parameters here, and basically give me an accuracy with a crossfold of 5. So it's going to try 650,000. Oops, too many. I did too many. Okay, there we go. I just wanted to add this one line, this max features line there. So basically, if we look at this, it's going to check 2, 3, 5, 7. And so doing 5 folds, this, if you did combination math, this would come out to 3,500. So we're going to make basically 20,000 different trees like this, and it's going to pick the most accurate one, sorting accuracy. So grid searches work well for sometimes small data set, or when you leave things running maybe overnight. That's one of the strategies sometimes I do at work when I have a little bit bigger grid search. I need to tune my parameters. I might just grab a small sample of the data, and then once I grab the small sample, do a grid search on that. So I'm going to let this run for a second, and then we'll continue on here in a minute. Okay, I wanted to kind of step that down to make it run so you didn't have to wait 15 minutes. But you can see even this ran 14 seconds with 800 fits. So it does take up quite a lot more time. From something that takes, I don't know, a fraction of a second to run, to something that now takes, I don't know, a few seconds to run, save. So just keep that in mind that grid searches, while they're very, very good at finding the best parameters, aren't always a reasonable way to do things. If I showed you cross-fold validation and regression, I wanted to show you grid search. They are commonly used, at least with small demo data sets, or at least proof of concepts, to kind of understand, where your data, where your parameters should be, at the end of the day. So you see before, we were at 72. We started at like, what, 68? Yeah, we started at 68.8. And then we were able to get up to 72 just by a few hand training. Let's see what the grid search came up with. The grid search came up with 75. And for the parameters I fed it, it said, hey, the maximum depth is 5, minimum is 3, minimum slit's 15. So what does that look like? That looks like this. So this is what the system recommends as one of the best grids with 75% accuracy, one of the best decision trees. I think that's still a little complex, and we can always try to train it down and make better changes. Maybe we only want max depth to be like 4, 5, and nothing more than that. Train it on that. And let's see how that affects accuracy. We're still at 75% accuracy, and let's see what that looks like. A little nicer, at least that's legible. We'd be able to use that. So that's your basic decision tree. Should work in Colabs, no problem. So please let me know if you have any questions on that. Now for the SVM homework. For the SVM, there's no homework. There's the SVM demo. Again, I did not author this notebook. I don't know really that much about this notebook, but let's run it all. So this will give you some basic concepts of the SVM, and I really like the way this notebook's designed. Okay, so we have a set of data in 2 dimensions right there. Okay, and we need to separate it. Not people going to Black Friday, people going to Black Friday. Non-diabetics, diabetics. Non-spam email, spam email. Now, we want to use a linear line to separate out those two. How do we do that? And he has some examples right here. A linear discriminator classifier would attempt to draw a straight line separating the two sets, and thereby creating a model for classification. For 2-dimensional data like shown here, that task could be done by hand, but immediately we see a problem. there's more than one possible dividing line, which can be perfectly discriminated between the two classes, which is true. Any one of these lines is fine for discriminating between these two sets. So really the question is, what's the best method? And that is basically to maximize the margin. Okay, support vector machines offer one way to improve upon this. The intuition is that rather than simply drawing a zero-width line between the classes, we can draw a line basically around the margins up to the nearest point. Let's go down here and see actually how that looks. Look at that. So now we have the line that basically is equal between the two of them. It has the highest margin between the two areas. Okay. Notice that a few of the turning points touch the margin here and here and here, as they are circled in the following figure. These points are the pivotal elements to the fit. They are known as the support vectors. It's where the name SVM, support vector, comes in. The key to the classifier success for the fit is only the position of the support vector matters. Any points further from the margin or on the correct side do not modify the fit. Technically, this is because these points do not contribute to the loss function used to fit the model. So the number and the positions don't matter as long as they do not cross the margin. For this example, we can plot 60 to 120 points and see there's no difference. See no difference. Okay. Now, what about this? And this comes to the idea of kernel hacks or kernel tricks, the more common probably term for it. So how do we, you see the line, how do we draw a line between that? Okay. So let me give you another example, an easier example, the one I had to learn. So I guess this could be considered a borrow trick. I really don't know. If I asked you to draw, so this is a one-dimensional line. Okay. I said, hey, I need a single vertical line to separate out all the red and blue dots. So I just need to draw a line. That's not going to do it. Well, I'm missing some of these over here. So how am I going to get a single line? I guess I can't, Richard. So this is where a kernel trick comes in. What if we were to move this, which is in 1D, what if we were to move this to 2 dimensions? Let me redraw that really quick. And now, see, there's my nice 2-dimensional plot of the same thing. See, red, blue, red, 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 blue, blue, red, red. So now, if you had to draw a line through it, could you? Yes. Look at that. The solution is do this, do a kernel trick. So that is what this this is trying to start talking about, is how to do a kernel trick. So basically we have a circle and we want to still have a linear fit, a linear line. So what we can do is take this 2-dimensional data and move it to 3 dimensions. Look at that. We could draw a line right through there. Line right through there. There's our margin. So they use this for face detection. As you see, they force it to make a decision down here. Predicting names with incorrect labels in red. So it thought this was Rumsfeld when it's actually Bush. It thought this was Tony Blair when it's actually Bush. So you can see here, here's the precision recall, the support. So again, this is why SVM is very popular. You can do some really unique things. Each image contains around 3,000 pixels. Yeah, it's often more effective to use some sort of preprocessor to extract meaningful features. Here we use PCA, which we might cover next week a little bit when we do clustering. I'm not sure if I'm going to do PCA or T-sign, but you can see basically, we can use this to detect features. An example of SVMs in action is to look at facial recognition. We'll use labeled faces in a wild data set consists of several thousand correlated photos of various public features. Okay. So that is why SVM is very important. This is a great notebook. Maybe just kind of breeze through it. I wonder who made this. I wonder if there's an about. Yeah, I just googled SVM collab. So again, you'd be surprised what just a simple Google can find. Those are decision tree, SVM are probably the two major ones. There's a few other types of classifiers that are super popular. I can cover more if you guys have questions. I just don't want to get anything too heavy and too mathematically complex and something that's going to give you a headache on the week that you had to kind of work on your data analytics project. Again, let me know if you have any questions. Please let me know by the evening of the 28th or the morning of the 28th. That's Saturday morning, I hope. Everyone's doing good, and I will talk to you later. Next week, it's going to be easy with Tableau clustering.